Hi guys, so I wanted to make this kind of a short video to maybe help someone down the line, because as you're learning about CNC machines, or machines that just generally move in the X and Y, Z coordinates, you really have to kind of understand how to control different types of motors. So it's important to know what you're working with. Here you see a DC motor, and here you see an encoder. That encoder acts as a sort of feedback for this DC motor. That feedback is important to tell the computer where the motor has moved in space. So this machine that you see right here is running off of LinuxCNC. Actually, it's running off that USB that has LinuxCNC on it. And the way it's controlling the motor is through a motor controller. Now this is the motor controller I'm using. It's an M54542L. Now let's move to LinuxCNC and see exactly how it interfaces to make this motor move. Alright, here's the Debian operating system. And I made a shortcut beforehand, but when you start this up for the first time, you won't see this. So go to the application menu up top on your top left, and then go to CNC. You'll see the LinuxCNC config picker. Click that. This will pop up, and all this is just shows you configuration options. So you have you know, axis, graphics. You have different boards that are supported, right? And then you can do by interface, and that's important because we're using a parallel port. So go to the parallel port tab, and you can find etch servo. This etch configuration drives two servo motors using a parallel port attached circuit. I'm just reading off of this description, and it uses an L298 dual full bridge driver to drive everything. You can load that configuration. Just click OK. It'll load up. Alright, so you're in your program, and now you're wondering, well, how do I connect things up to make my circuit on the workbench work, right? Okay, so you exit out of this, and then you go to your home, you go to LinuxCNC, you go to your configs, and then you go to your configuration folder, and then you should find your HAL file. And then in that HAL file, you'll find the appropriate pins that are used. So here we have X direction on parallel port pin 2, and so on. So one thing you should notice out of all of this is that when it comes to driving a DC motor in this configuration, they use 2 pins, right? And that's because the motor driver, the full bridge that they're using, works on a truth table, or works on 2 inputs, right? And for 2 different inputs, then you get a certain output. That output being how the electricity flows to make the motor turn in a certain direction. And so they're using those 2 pins to drive that motor, but they're also using a third one. A third pin for a pulse width modulation signal. And that signal is important because that signal actually enables the motor to go, right? To turn on, actually. And that controls the speed as well at the same time. So for the encoder, I just have a simple emitter and receiver. So that's 4 wires in total, because 2 wires for the infrared LED and 2 wires for the sensor. And so really you just need to power the encoder, and then once you power it, you connect those other 2 leads from that sensor to these pins that are specified right here. So this is encoder 0, right? And you have phase A and phase B. Those correspond to pins 10 and 11. And I connected my leads from that sensor in the encoder to pins 10 and 11, and it worked just fine. I will show you how this connects on the actual data sheet. I printed out this block diagram because this is really important to see visually. So we have two outputs here and we have two outputs here. This motor driver can drive two motors, but let's just focus on one block, right? So this block has two outputs for one motor and it has two inputs, right, for one motor. Based on the inputs, the outputs control the flow of electricity to make the motor turn in a certain direction. Now, you can notice right here is the enable pin. So this enable connection goes to this piece of logic circuitry. This is not important to know if this is an AND, XOR, or different types of logic. Really, what you have to notice here is that this enable connection is simply connected over to the base of this transistor. Meaning that this enable pin, all it does in conjunction with the inputs is turn on the base of this transistor to make the power flow through the outputs, right? That should make sense. Now, the motor controller that I have, it uses two outputs, right? And it uses two inputs. And this is just like one full bridge, not a dual bridge. You can notice that we don't have any connections for an enable pin. And that's because everything's done internally and they just don't provide that option. And here's the truth table, as you can see, that it runs off of. What we know from looking at the other schematic is that what the enable pin does is simply turn on or turn off the power going to the motor. So what if, to make an enable pin for this circuit, what if we simply routed all the power pins to one pin and then simply took that pin and connected it over to a switch that would be controlled by our enable signal that we have configured in LinuxCNC. That was my idea, and actually, I did it. Alright, so this is most of the connections. Now, this is a lot of wiring, and I don't want to really explain like all the minute details because that could end up in a long video. So I'll just do it in blocks. So here we have a 5-volt phone charger. That just provides us 5 volts to power the encoder with, right? Because it needs some kind of power to transmit that signal over to the sensor. Now, speaking of the sensor, that sensor is connected over by these two wires. And I know what you're thinking. How the hell, out of all these wires, do you find the appropriate pins to connect the sensor to, right? Okay, well, I'll show you. So hopefully you can see this, but on the parallel port that I'm using itself, there are numbers right here, tiny numbers that indicate where all the pins are. And you have another set of numbers on the top here, but because of the lighting I don't think you can see that. But you can probably just make out these numbers on the bottom over here. And literally what I do is I take a piece of breadboard wire and I connect it to any pin that I need to find, and it should, without much effort, just, yeah, stick in there, right? Should fit. And then I connect this end over to my multimeter, and I just do a simple continuity test. I actually literally test all the wires, and when my multimeter makes a beep, then I know I hit the right wire. So we left off at the signal wires that connected to the encoder sensor, and now I'll zoom in right there on this yellow and this green wire. They're connected to pins 2 and 4, and that middle blue wire, if you can see it, it is connected to that pin 3, the PWM signal. So basically I just found those pins by doing the same continuity test. And those LEDs, if you're wondering, that's from a separate project, so don't pay attention to that. So pins 2 and 4, they connect directly over to the motor controller. But it's a different story for pin 3. Pin 3 is the enable pin, like I said, and pin 3 has to go through this N-channel MOSFET. So the board is irrelevant. I just kept the MOSFET on there because I was too lazy to take it off. But this N-channel MOSFET is designed to turn on at a fairly low voltage. I think it was maybe 4.5 or even lower. But in any case, it was suitable because I hooked up one of the breadboard wires to the positive terminal, and I routed that through the drain of the MOSFET, and then this is the source, and I routed that over to the power supply. The power supply is giving like 11 volts of power. And then for the gate that's over here, I actually connected that directly over to pin 3. And so in this way, the power is interrupted. All the power that goes into the motor controller is interrupted by this small N-channel MOSFET. I checked the specifications of this MOSFET, and I made sure that it can handle the 10, 11 volts and also the current, and it seems to be okay. You also have to make sure that it can turn on with the PWM signal that's on pin 3. But if you have all that covered, then it should work. I'll demonstrate this now. So I found to make things work and for the motor to not run off on you, first enable encoder. Then you have to turn on your machine. The last thing you should do is apply power. And there you go. Okay, so once you open your program, you will see something like this. The reason why I have a really long rectangle is because I modified the x-coordinate soft limits in the HAL configuration file. And that's because it gives me more room to play around with the x-axis once I have the motor moving. Alright, so this is the etch.ini file, and here you will find all the configurations for the axes. So the first axis, which is the x-axis, you'll find right here, and you'll notice that the min and max limits are fairly low. You can change these, and I'll do it right now. So you can change these, and you'll have a bigger x-axis to work with. You'll also find the base period and the servo period in this ini configuration file. And these are extremely important if you want to tune this servo motor and get the least possible latency. To see what specific latency your machine has, you can go into your terminal and then type in latency test. And this will bring up a window that will automatically start testing the latency. Once you have these numbers, you can start to tune your configuration file. You can input these numbers into here and see if the latency improves on your machine. Now keep in mind we're controlling the motor via software, and software can only go so far until you encounter serious latency issues that will make it difficult to control the motor in real time. So to solve those latency issues, you might want to consider proprietary hardware. However, buying hardware may not always be friendly to your wallet. So in a pinch, this software option might do the trick, and it's always nice to experiment with it so you can have it as a learning tool, which I'm doing in this case, because I'm learning about how to control motors via encoders. Before you apply power, make sure you turn on your machine and you have the controls ready. Once you have the controls ready, you can then apply the power. And once you have the power applied, as you can see over here, the x-axis is jittery, it's shaking, and that's just, the motor shaking, trying to correct itself. But from here you can, actually, before you even start moving it, you can change the jog speed up to the maximum limit just to make the motor move a bit faster when you're controlling it. And as you can see, the motor is moving on the screen, and it's also moving in real time as well.